Nonlinear trajectory tracking with a 6DOF AUV using MRAFC controller. ID 9259. Authors: Master Lugue Fenco and Dr. Gustavo Pérez Zúñiga. Pontificia Universidad Católica del Perú, November 2024. Problem statement. Climate change, the greenhouse effect and environmental pollution are driving forces behind the deterioration of ocean health. New technologies such as underwater robots are used for marine exploration. AUVs are part of underwater robots. Efficient ocean monitoring using AUVs must take into account the nonlinear model of the system and the complex characteristics of the ocean. Currently, conventional controllers presenting inaccuracy in the trajectory or instability due to intrinsic disturbances of the surrounding medium. Contribution. Design of a reference model adaptive fuzzy controller, MRAFC, for an AUV. The control strategy is based on a combination of fuzzy system theories using the Takagy Sugeno model, adaptive control laws and Lyapunov's nonlinear control theories. Since the matrix P is the common matrix of the linear subsystems, calculated using numerical optimization techniques and also starting from the tracking error equation, we can obtain the equations of the adaptive law, as shown in equations 1 and 2. The implementation of the equations of the adaptive law is shown in Figure 1, where, previously, the nonlinear model and the reference model have been transformed using the Takagy Sugeno technique, both generating a difference whose vector E is one of the parameters that feed the adaptive law. The next input vector in the adaptive law is the vector R obtained apart from the difference of the desired trajectory and the reference model. The parameters K and J resulting from the adaptive law directly modify the fuzzy law whose output vector U acts directly on the nonlinear model of the AUV, resulting in convergence in the desired trajectory. However, the tracking performed by the AUV generates a steady-state error due to the linearization of the system, which can be compensated by a PID control, as shown in Figure 1. Results: ideal conditions. The results shown below are obtained by applying LQR and MRAC test controllers together with the proposed MRAFC controller when the system is not exposed to external disturbances and noise. Observing from image A, instability states from time 30 for the LQR controller, while the MRAC and MRAFC controllers converge on the desired trajectories. Similarly, it can be observed from image B, the behavior of the output vector, where the LQR controller generates the chattering effect in the attempt to control the AUV. In image C, the path of the trajectory is shown in a 3D view, observing that the only controller that does not converge is LQR. Quantitative results are shown in image D, based on the RMSE performance indicator. Results: with disturbance. The following test is based on applying a perturbation to the system from time 10 to time 30, obtaining the following results. Image E shows the results for the ETA vector, observing now that the instability is for the LQR and MRAC controllers, while the MRAFC controller manages to converge without problems to the desired trajectory. Image F shows the time response of the output vector, observing now the chattering effect in both controllers, LQR and MRAC. Image G now shows that the only one that converges to the trajectory is the MRAFC controller, and this is supported by the quantitative analysis of image H through the RMSE performance indicator. Results: with noise. Finally, the next test is based on adding noise to the system and evaluating which of the three controllers is the most robust. Then, observing image I and J, we can observe instability in the state vector and in the output vector for the LQR and MRAC controllers. But the MRAFC controller maintains convergence, noting the effort generated in each of the variables of the output vector, which are now not smooth and continuous signals, but on the contrary are observed to be very variable in time. Image K gives us a better view of the path, showing the convergence of the MRAFC controller. This result is supported by the quantitative data in image L, concluding that the controller in different scenarios remains stable and robust. Conclusions. A robust MRAFC controller was designed for a 6DOF AUV. A mathematical model was developed for the nonlinear system of the AUV, considering uncertain system parameters and the dynamic complexity of the ocean. An MRAFC controller was developed based on the Takagy Sugeno technique, on the nonlinear Lyapunov control theory and LMI's numerical optimization, to ensure the desired navigation. A comparative analysis was performed based on performance indices applied to the LQR, MRAC and MRAFC controllers, obtaining a better result in the MRAFC controller in the presence of disturbances and noise. It is concluded that the MRAC controller is capable of converging, following the desired trajectory and establishing the minimum tracking error in adverse conditions. Simulation.